Hello, everyone. I'm totally honored and privileged today standing in front of such an august gathering and presenting of my journal. I'm Tina Bedi. I'm a managing editor of SN Computer Science journal, and I recently joined 2 months back to this journal. Today I would like to share small stories of 2 success stories. And the first story is, I just put on, of a small bookshop that evolved to an extent that it got merged with 2 special brand names together and come up with a special brand name that is called Springer Nature. And the Springer Nature is now started in May 2015, and now it's with different brand names, special imprints. We are working on the different imprints such as Nature Research, Biomed Central, Springer, Scientific American, and Palgrave Macmillan. We are into existence from over 175 years into publishing, and we are privileged to publish many renowned authors like many of you, and we are also published with so many Nobel laureates and field medalists. You can see the names of these big personalities which are published with Springer Nature. And to take care of this responsibility, we have around 13,000 employees in 50 countries, and which are responsible for working on 3,000 journals across the globe. This is our journal, and the second story start with this journal. And as the computer field is now growing, and it's a very exciting field, and in every discipline, the computer field and informatics and all this is used, from biology to humanities to social sciences to statistics. All of them are using the computer science and the technology. To take up this challenge, our management had decided to come up with a special imprint, Springer and Nature, and then come up with this journal. And here we are, SN Computer Science, under the leadership of Professor Errol Glenbey and Professor Umapada Paul. And this journal is freely available till 2021 December. Yeah. So we have a very eminent editorial board with us, from Rama Chillappa to, you can see, Vincent Poor. All these are eminent authors worldwide, eminent researchers. They have joined together to make our journal more prestigious. We have also, till date, we have so far 6,000 submissions, and very soon we are going to publish around 50 articles, first 50 articles in our journal. And we are very keen to make our journal for the people, by the people, and for the computer science community. And this journal encourages partnership with the conferences to publish in form of conference best extended papers. And we are also inviting many institutes and departments to publish their niche within the journal, to come up with 1 or 2 issues per year. And we are getting support from Professor Glenbey all over throughout the journey. And we are, this journal is giving wings to the new researchers. And we are very positive about this journal. Only a 3-month journey. In May 2019, it has just started. And we are, making this, join hands together to make this journal a big success. That's the only thing. Thank you very much. Yes, I have put on flyers. If you have any questions, you can come up with the questions, and you can even...
2 years, Springer has open access to Thanks very much.
Thank you. Thank you very much.
I'm going to describe the tools, and it will be, there will be point processes, stability issues, various mean field models, and then in the queuing setting, various particle system notions. Okay, so let me start with motivation. So this is about space-time interactions, which is a very broad topic. So in wireless, which is the initial motivation, there is now a sort of well-known setting for handling using stochastic geometry to understand interference fields in terms of short noise processes, and this was later mixed with cellular structure. There are also various queuing models to take into account, various type of join and leave, birth and death in queuing. I've given a few citations of this, the early work on this topic. And content of this lecture is really about such dynamics within the geometry setting, which is necessary for wireless. So we start with part one. So I'll describe the cellular a bit later, but let's look at D2D, infrastructure-less wireless network. It will be a Markov model. Everything will be Poisson exponential, and technical tools will be point processes and mean field approximations. So this is an artist view of the dynamics. So you have a Poisson rain of dipoles. Here is a dipole, right? You see it's a sort of directed vector that fall from the sky on a domain D or S, and each dipole, the starting point of the vector is transmitter, the endpoint is the receiver, and each dipole comes with a file to be transmitted on a wireless link. And what happens is that if these things fall from the sky as a Poisson rain on this part S of the Euclidean space, which will be a compact here, the key thing is that the death rate, which is the chance if the files are exponential with which such a link dies or disappears, is linked to Shannon channel coding theory, that the rate at a given point, this receiver will be proportional to the log of 1 plus the signal, which is the strength on this link, over the noise plus the interference. And the interference, this is the receiver I look at for this link, will be created by all interferers or all transmitters that show up at that time in the configuration. Okay, and the key thing is that this dynamic, it's a dynamic, so these dipoles from the sky, they transmit their file, and then they leave, right? That's the story. But as you see, the death rate is a function of the current configuration. So you cannot disentangle geometry and the dynamics. That's the interesting thing, and we will see how in a second. So the model features, say, torus, links that arrive according to a Poisson point process in time-space. Each arrival has an exponential file with L bits in mean to transmit, and the point exits after the transmitter finishes transmitting his file. Current configuration features a random measure, phi t at time t, which gives the location of the points in this torus. A key feature, as I said, is the interference. So it's a short noise of the configuration. So you have an attenuation function L, called the path loss function, and the interference at locus X is the sum of, so I will make as if dipoles were very short, so that interference at the transmitter is close to interference as at the receiver. So I mean, it's not a limitation, just to make exposition easy. And so the interference at X, given receiver, is the sum of the shots, namely the powers transmitted by the various transmitters in the configuration, attenuated by the function L, which I described a bit earlier, the path loss function. And distance here would be distance of the torus. Okay, and as I said, the speed of the file transfer by link at X in configuration phi is given by the Shannon formula. So B would be the bandwidth, and N would be the thermal noise, the power of the thermal noise. Okay, you recognize log of 1 plus SINR. Okay, so there is a birth and death master equation, which I will not describe, but in detail, because that's not what you can handle in order to understand what's going on. But typically, it says that a dipole leaves at the first time it has received sufficiently many bits to have exhausted the file size L that it has to transmit, right? And the key thing is that you can't use these techniques of, say, Markov or this fixed point equation in order to solve the problem. Okay, so nevertheless, we can use the Markov structure of the point processes to get simple representations, and you will see rate conservation equations for this, the steady state when it exists. Okay, questions are existence and uniqueness of the stationary regime, characterization, that's where the sort of mean field will show up. Okay, so first result, let's take the constant A, which could be infinite in some cases. If, for instance, the function L has a pole, it's just the integral of the L function over the torus. So if lambda is more than lambda C, which is B over log 2 L times A is this constant, then phi t admits no stationary regime, so it's transient. The phi t is a Markov chain on the space of counting measures. And if lambda is less than this constant, then under technical assumptions, which are the boundedness and monotonicity of L, then phi t admits a unique stationary regime, so it's actually ergodic as a Markov chain on counting measures. Okay, so I will have no time to give proofs, and so I could discuss that with pleasure. A corollary of that is that if the path loss model is the famous power law, which is used in coming from physics, so r to the minus alpha for alpha more than 2, say you're in a plane, then there is no lambda such that the system is stable. The main qualitative result is that there is clustering. This point process will be clustered in the sense that if you take any function f, which is non-increasing from the real numbers to themselves, the positive real numbers themselves, then if you look at the short noise of the configuration, phi in steady state, when it exists, of course, is not Poisson. Because the rain is Poisson, but as you understand, what happens is that when there is an aggregation of customers falling in the plane, then the interference becomes big, therefore the rate becomes lower, and therefore people have a tendency to clog, right? And this is a clustering thing. So, and it results into the fact that seen from a typical point of the torus, this is this palm expectation, the shot noise is bigger than the shot noise or for the F function of the stationary regime in space, right? So, okay, so this follows from palm calculus plus FKG type inequalities. So the steady state point process, when it exists, is clustered. And the interpretation is this entangling between geometry and dynamics. The steady state interference measured at a uniformly random chosen point of the space, namely a link, is larger. It means that at a uniformly random locus on space, right? So actually things clog and cluster. Okay, so the key observation is that here dynamics shapes geometry, because indeed dynamics makes that people will stay longer at areas which are clogged or clustered, and geometry shapes dynamics dually for the same reason. If in an area which is clustered, people stay longer, and still things are such that under the conditions that I said, integrability of A, this admits a stationary regime. These are pictures of the clogging, and you see there is clustering. It's not a Poisson. This is steady state on these torus. Okay, quantitative results are this Poisson first order heuristic, which is a mean field actually, and the second order cavity method. And here we look just at computing beta F, which is the first order density of points, and beta S for the second order density of points in steady state. So everything is based on conservation laws. We discussed conservation laws this morning. So let's look at one of them. And okay, so pick a small locus in space. What arrives per unit spine this locus? Lambda, the Poisson range, times L, the mean number of bits of a file. What leaves, assuming that there is a point, say at 0. So first there should be a point. So this is beta, the unknown density parameter, times the expectation of the Shannon rate. Right? This is the mean number of bits that leave this locus X, which you express like this. The Poisson heuristic, so the key thing is this palm expectation, which is seen from a typical point, is to pretend, and there is a mean field interpretation of that, that you will neglect the palm expectation here. And in that case, this fixed point equation becomes computable. So it leads to a fixed point equation in terms of the parameter beta F. Here you see beta F showing up here, which was there, right? And here in the expression, which comes from the shot noise of the interference, the distribution function of the interference, the Laplace transform of the interference. And so in this Poisson approximation, approximating palm by the stationary distribution plus 1 point is tantamount to Poisson. So you use this formula that the expectation of log of 1 plus x over y plus a as this nice integral representation in terms of the random variable or the Laplace transform of the random variable I, which is the shot noise. And since you are in the Poisson realm, you can compute this at this integral in terms of the unknown parameter beta F. So these are these type of things. And so there is a second order heuristic. I will perhaps not spend much time on it, but so you refine that by fixing, getting another more refined fixed point equation, which is a sort of cavity method, which I could explain a bit later, but which improves the Poisson approximation. Okay, so let me skip that and give numerical results. So this is lambda over lambda c. Lambda c is the exact stability condition. And you would see the simulation with their confidence interval in blue. The first order Poisson heuristic, which is tight asymptotically for small intensity and large intensities. And the second order approximation, which is quite good, this cavity method is quite good representation of the steady state densities. Okay, let's move to the second part, the cellular thing. So it features again a single cell and the uplink. We look at the low SINR thing. So we linearize the log. And tools will be again stability. You will see a new phenomenon, metastability. Again, RCP and first and second order methods. So the system model features a single base station located at the origin with an association region which is a compact D. For instance, a ball centered at the base station, but could be anything. User arrive in D according to a Poisson range of intensity lambda, same feature, and same story, exponential files. When the user arrives in the cell and has transmitted this file, it vanishes, like in queuing. The dynamics is again a Markov spatial burst and its process, phi t, with now state space counting measures on D. Interference now has a slightly different form, so because you measure it at the base station. So if you have a configuration phi, the interference created for user X, or with respect to user X, is the sum of the attenuation seen from the other users at the base station, say at 0. And here, as in wireless, we use a power control, which tries to attenuate the effect of the far field phenomenon for far users. So you compensate the L function by L to the minus beta. So if beta is equal to 0, this is a constant. If beta is equal to 1, you give this power so as to compensate from elongation of a certain user, or distance to users, right? And so same story as earlier. The rate at the base station for user X is the log of 1 plus SINR. I has this new form. Okay, so stability condition. So again, if and only if. This is the constant B over log of 2L this time. So interesting thing is that under certain assumptions on L, which are again continuity, monotonicity, and boundedness, lambda C is the stability threshold. So if lambda more lambda C, phi t is transient, otherwise it's ergodic. And as earlier, stability is oblivious of thermal noise, and stability here is also, so you remember that the shape was not importing, only the integral of the L function was showing up in the stability condition. Now this has disappeared because you are on this compact. Okay, so here is the equation of the rate conservation principle, the same one as I was describing a bit earlier. So let's call lambda of X the density of the steady state point process phi under the stability condition. Okay, and now, say in this ball, there will be more users at the edge of the cell, right, because they stay longer, they have this L, and so the density depends on distance, actually, and so it depends actually on the norm of X. So, but in principle, you can write conservation equation without saying that. This is the arrival number of bits in a small area around X, and this is the density of X at X times the rate out of X, right? Which is again in terms of a palm expectation with respect to the point process. And so things have changed a little bit because I've used the power control. Okay, now Poisson heuristic or first order heuristic is the same type of shape. So actually here you get that the fluid or first order density gamma of X, which is the analog of the beta F of earlier, as a representation as a constant divided by L of norm of X to the 1 minus beta. Beta is the way you tune the power mechanism. And the Z star constant is a solution of a consistency equation, which is written here. And where you see actually Z and Z here in the exponential. So actually it looks a little bit, well, I won't say too much on this fixed point equation, but it is linked to some special functions, the Lambert function. I will not describe that too much. The key thing is an interesting plot which already starts to explain is that if lambda is less than lambda c, then this fixed point equation has a unique solution. There is a lambda m which is given here, such that if lambda is between lambda c and lambda m, above stability, this equation has two solutions. And since it's a mean field, it's a sign of metastability. It's a meta theorem for the physicists that if the mean field exhibits two solutions for the consistency equation, then you should have metastability. And indeed, there is metastability. So this is depicting it. So here you have the same type of plots where you would have, if you want, the z, which is proportional to the mean number of users, and the lambda. So if lambda is less than lambda c, which is plotted here, then there is unique solution. And if you are in between lambda c and lambda m, you find two solutions. And typically, like in the old ALOA analysis, this stable point would look like this fixed point would look like a stable point, and this one like an unstable point. And so random fluctuations will drive you one day from here to here, and then you go down the hill, and the end goes to infinity. So this is sort of the picture that you get from this analysis. And indeed, so when we simulate, we find this very interesting phenomenon, metastability. You must have seen things in physics and metastability. You see, when you take this glass of water, this bottle, you put it in the fridge with the right temperature cooling. So you have to cool very, neither too quickly nor too slowly. And so you lower temperature at the right pace. And so it should be ice, but it's not. And if you do this, then it freezes instantly. So it has been seen for ALOHA. There are well-known things on ALOHA and that. But here, that's what it says. You simulate, you see the time scale is 10 to the 7. So you see this birth and death process, like the picture said. So it behaves quite well. And suddenly, there is a random phenomenon, which is like the small things that you would do on this water, and then it freezes. Namely, it goes to its natural state. It moves to the other part of the curve. And this curve is very interesting because it's very different from the other one. The other one goes down to 0. This one goes down to 9. So it's very, very different. Okay, so these are the first and second order heuristics on this dynamics. So you see that actually, the first order heuristic here depicted here, for instance, would be rather bad, but the second order is quite well. So we can actually further go to understand what's going on practically. Okay, so let me go to the queuing now. So these things are spatial dynamics, so they look perhaps a bit odd to you. But let's look at the discretization and the version of it, which is in terms of a particle system, an infinite queuing network, if you want. So this is again an artist's view of the dynamics. So a small square is a part of the Euclidean space. So it would be R2 if you want. And so here you will set a queue. Qi will have a number of customers, say X, right? And here the X is depicted by the color. Okay, so this queue has X pink, this queue has X yellow, and so forth. Okay, and the interference at a given queue, say this one, which is the taxing, there is a queue here, there is self-interference because it's a discretization of space. There would be A naught, which is like the L function locally, and then you would have A1 and the neighbors would interfere with this one, A2 and blah, of the X variables, right? This is interference. Okay, and the rate at a queue is mu, which is X, because there are X guys which compete for departing, so sort of processing thing, with a speed which is 1 over the noise plus interference, which is this sum I. Okay? Very good. So this is the math of it now after the artist view. Qi in ZD has state xi of t, which is an integer at time t. Arrivals are ID Poisson of rate lambda in that queue and in every queue. Interference sequence is non-negative, symmetric, irreducible. I don't describe what it is, say positive everywhere. Service disciplines is a generalized processor sharing with a rate which is proportional to xi and inversely proportional to the shot noise of the configuration, right? So you recognize a generalized processor sharing queue with positive correlation, well, I would say negative interaction. If your neighbors are very busy, then your rate is very slow. But if you have many customers yourself, your rate increases proportionally to your population, right? So this is the SINR processor sharing queue if you want. Okay, theorem. It works for the whole ZD now. That's the particle system version of it. So if lambda less than 1 over the integral of the A function, you recognize the A parameter of the first slide, the network is stable. So you can't say positive recurrent because it's infinite dimensional. And the weak limit is the minimal solution of the stationary regime, right? So what I call weak limit, so what we call stability, now you start the system empty at time 0, and you want to check whether there is weak convergence of the state of any finite set of Qs as t goes to infinity. So these are coupling from the past technique. And you can prove that the weak limit, when it exists, is this minimal solution. And this stability condition is sharp. We have current proof only in special cases, but we are sure it's the case. So it's if and only if up to criticality. And now that's the new thing that we are very proud of. There is a closed form for the first order moment measure without the mean field approximation. And here is the result. So the weak limit of the steady state in this infinite particle or queuing system, when it exists, is given by E of x naught. So everything is invariant by translation, is lambda A naught divided by 1 minus lambda times the integral of the A function. Okay? And so the proof is these are Palm calculus techniques. It's quite involved, actually. Again, one uses association to prove that the coordinates are positively correlated. And we find it remarkable that it is a system which is not in its mean field approximation, non-reversible, infinite dimensional, and not asymptotically independent. Qs, local Qs are locally positively correlated in the steady state. One could find the equivalent of the first moment measure in closed form. So they are using these results, but how much more time do I have? I'm not sure I have to go. I started, how much more time? Over? Okay, good. So let me skip uniqueness. We have studied uniqueness and the domain attraction of the minimal solution. There may be several solutions. So this is infinite dimensional, and so if you start from bad initial condition, there are many counterexamples that we have in the paper. So let me conclude if my time is over. So we have an exact representation of space-time interactions in wireless networks. As I said, these dynamics are sort of not so easy because they are not reversible, no product form, no asymptotic independence. There is a notion of dynamic capacity which encompasses Shannon's theory and dynamics, which is perhaps interesting. They create clustering or positive association in the queuing realm. We have good mean field heuristics in general. The first order, which is essentially a Poisson approximation, and the second one, which is a cavity method. Surprisingly, in the low SINR case, there are exact analytical results on moment measures. They exhibit metastability as soon as you introduce various types. And there is a particle system infinite dimensional version of these dynamics with closed forms also.
When you have instability, do you have zero throughputs per square centimeter per unit space, or do you have a finite throughput, a local finite throughput per?
Well, actually, no, interference will go to infinity, and so in that case, you will have zero throughput in the end. Because actually, even think of the cellular case. Okay, so users will start accumulating at the boundary. And their interference starts freezing, and it freezes inwards, and the whole thing.
So it's zero throughput.
Asymptotically.
Yeah,
right.
Yeah, yeah.
But you get still throughput in the prelimit, right?
Yeah. With respect to that, suppose that each station had a timeout.
Yeah.
Then it would completely change the situation.
Yes, right.
And all stations do have a timeout.
Yes, of course, yeah.
So what would be really interesting, I think, is to look at how the timeout affects the result. That is, what kind of throughputs you get with what kind of values of timeout. Because that's the parameter that you can actually adjust. You can't adjust your neighbors, presumably, but you can adjust yourself. And the other question I had was about the queuing model, or perhaps even the single single raindrop model, where the raindrop withdraws from the channel.
The raindrop?
The raindrop
Yes.
withdraws from the channel, goes up into the air again, and then after some random time drops back. So it's the Aloha
okay.
control.
Okay. Yeah.
So are there self-stabilizing simple controls?
So when you start adding this type of dynamics, things are still feasible in the mean field, and we are looking at them, but so it's ongoing. So, but in a sense, I mean, there would be a lambda, which would be a fixed point of an equation, like in the Aloha case, right? That you give up and come back later. And so if you would assume Poisson, you would integrate that in the lambda and get fixed points. So the mean field theory works. The small miracle of the exact solution for the dynamics for the first moment, I don't think it will work. But for the mean field, yes. Which surprisingly reveals the essence of the problem, namely the exact stability condition in a few lines and the existence of two solutions and metastability in the cellular case. Right? So it's quite amazing.
Thank you. Any more remarks or questions? If not, thank you again. Yes. Yes, so the floor is yours, Maria Carla Calzarosso.
So good afternoon. Thank you very much, Gerald, for the invitation. I'm very honored to be here to give a talk to this special edition. Sorry, thank you. To this special edition of the conference to celebrate the anniversary of the French and Polish collaboration. The talk of today will be about resource provisioning in cloud environment under uncertainty. How does it work here? Okay. So here is the outline of my presentation. After a background that will try to motivate our work, I will present the modeling framework that we have proposed and the optimization problem that we have formulated. I will then present some of the results that we have obtained to validate our approach, and finally I will conclude the presentation with some remarks and future directions. So here is the background where I want to convince you that this problem is very important to be addressed. We'll know that cloud technologies are very important nowadays because they offer cost-effective solutions for deploying services applications. In this framework, cloud users are mainly willing to identify the best possible solution for deploying their application and satisfy at the same time their desired service levels. Unfortunately, the decisions about provisioning and scheduling are very, very challenging. And the challenges come from different problems, different aspects. First of all, these problems, these decisions have to cope with very many possible choices. We have on the market many different providers. Each provider has a wide variety of resources characterized by different performance and different cost, and so users have to choose from these diverse resources. In addition, we have two problems related to workloads and cloud environments. First of all, the workload characteristic varies over time. For example, we have a workload that has phases with the different requirements. And similarly, we have the performance of cloud resources, which are usually affected by variability and by fluctuations. And this is mainly due, for example, to the fact that we have virtualization technologies together with, for example, problems of collocation of incompatible workloads on the same physical machines. So in this scenario, what we have tried to address is the problem of finding the optimal mapping between tasks and cloud resources. So given an application that is, consists of a certain number of tasks with precedent relationships, the problem is to find the mapping between these application, these tasks, and the resources that have to be allocated. So in this case, we have to decide which resource have to be allocated, and the mapping between the task and the resources that have been selected, and as well as the additional precedent constraints that are induced by this mapping. So this is the problem. So the modeling framework that we are proposing consists basically of three main actors. We have the users who have some specific requirements about the quality of service that they are willing to achieve, as well as the cost that they are willing to pay. We have the workload and the cloud, the workload with their own characteristic, and the cloud, again, with the characteristic and the performance of the resources. And the point that we want to achieve is to define the resource provisioning and scheduling plan that fits the requirements and the specification that we have given above. So what we have here, we need to formulate an optimization problem, which takes into input the specification given above and provides the plan that we want to achieve. And for the moment, we have nothing new, because this is a typical problem that has been studied many, many times, because this is a topic that has been widely addressed in the literature. So what is new here is that we focus on the characteristic of the clouds and the workload. And this is the part that we think is affected by uncertainty. So the information that we have are not stable, so are not fixed. There are variability, and so this is the part that is affected by uncertainty. And we want to model this uncertainty, explicitly model this uncertainty into the optimization problem using what we call a sort of probabilistic evaluation, and we'll see the details in a minute. So what we have in summary. So we have we specify the characteristics of the individual tasks in terms of their service demands, for example, the computation demand or the communication demand of a task. And we model these characteristics with demand as random variables that are described by their probability distribution function. Similarly, we have the performance of the cloud resources, the cloud infrastructure. For example, the processing capacity of a VM. Again, these specifications are described by random variables with their own probability distribution functions. Of course, the monetary costs are not affected by instability, so they provide a set cost, and we need to pay. We must pay the cost that has been set. So this is not affected by instability. However, what we obtain as overall execution time of the application as well as cost for deploying the application are random variables, again, because they are obtained as a combination of random variables. So what is our probabilistic evaluation? In our probabilistic evaluation, we broke down the execution time of the individual tasks in three components. So we consider the computation time that the application spans for computing, that is the ratio between the demand and the speed of the virtual machine. Similarly, we have the communication time that the application spends in exchanging data, that the task spends in exchanging data with other tasks, and the data transfer that again is related to the fact that tasks need to read some inputs and write some outputs to external storage. So these are the components that we have. They, as you can see, are basically defined as ratios between random variables. For example, if we go back to the scheduling plan that we have seen before, from here, from the single components, for the individual execution times of the task, we can have the overall execution time of the application. And in this case, we have some sum of times that take into account the fact that we have sequential tasks that are executed on the same virtual machine, As well as we have to apply maximum operators to take into account the fact that there are additional precedent constraints that were not present in the original DAG. Similarly, we have the application cost. That is the expression that we use to compute the application cost, the cost of the task for the individual of the application, where we have the various components, again, related to the computation, the communication, and the data transfer. And the overall cost, of course, is the sum of these components. So this is basically the idea that we have. So what we need to do in this probabilistic evaluation, this probabilistic evaluation requires some algebraic operations on random variables. According to the distribution that we will use, we will never find some closed form. So we either need to resort to some numerical evaluations or to Monte Carlo simulations. So these are the two ways to include this probabilistic evaluation. From these values, we formulated an optimization problem. So the idea is that we want to minimize the expected cost associated with the application. And we have a constraint, and we put a constraint on a deadline. So the user is willing to execute the application within a given deadline, and we associate a probability with this to violating or satisfying better the deadline. So this is a single objective optimization problem with the deadline constraint. The problem, as we know, this is a combinatorial problem. The solution space grows exponentially with the number of tasks and number of VMs, possible VM that can be allocated. And so in general, the exploration of this space could be based on heuristic or meta-heuristic approaches. We use in particular the genetic algorithm that need to be appropriately customized to the problem that we have to solve. So some quick ideas about the experiments that we have done to test the approach. So basically we consider applications consisting of tasks organized in two sequential phases. So the task of the first phase read some input from an external data storage and then send their outputs to all tasks of the second stage. And the task of the second stage sends their output write their output to an external data storage. We consider a cloud environment consisting of a multi-cloud environment where we have private cloud infrastructure as well as infrastructure coming from two providers. We model the variability in the performance of the cloud resources in terms of well-known distribution. In particular, we tested uniform, half-normal, and Weibull distribution. And we set these values about the deadline and the probability of satisfying the deadline. What happened? Okay. So these two diagrams give you an idea of the results that we have obtained. On the left-hand side, we plot as a function of the variability factor ranging from 0.1 to 0.7, the probability of satisfying the deadline. I remind you that we set the probability of satisfying the deadline 0.8. So this basically is a proof that the method that we apply works. But what I want to point out is that the probability that we obtain varies from according to the distribution that we obtain. The colors, as you can see, represent the three distributions that we have tested, so half, normal, Weibull, and uniform. What is more interesting is the diagram on the right-hand side, which represents the cost for deploying the application when variability goes from 0.1 again to 0.7. As you can see, as the variability increases, the cost for deploying the application also increases. And this is due basically to the fact that when the variability is larger, gets larger, we need more powerful virtual machines or a larger number of virtual machines to cope with the variability and satisfy at the same time the deadline. It is also interesting to point out that when the variability gets even larger than the value that we have is shown in the diagram, we can have a situation where the problem does not have any solution. So we cannot find any feasible solution that of the optimization problem. I'm too fast. I don't know. There was a diagram here, but it disappeared. So since I'm running out of time, so the other point was the diagram that disappeared here. I don't know why. We also tested some. We also made some tests to check the impact of the problem size. So as the problem size gets larger, so what happens to the time, and what happens to the expected execution time, and to the 80th percentile of the execution time. Anyway, no problem. So in conclusion, what I can say that the problem that we address, we believe that it's a very challenging and very important problem, and it is also very important to have the possibility to give the users the possibility to estimate in advance the most appropriate resource settings that could be allocated to their application. And also the fact that uncertainty and variability are explicitly included in the formulation of the problem and in the evaluation of the problem is also very important, because we all know that whenever we have cloud resources, we have nominal performance, but this nominal performance is seldom achieved. And so we need to take into account this explicitly. We are also working to extend this approach to include more generic workflows, not just the two stages workload that we have considered in this study, and also more complex environments where we have a combination of cloud and edge environments, and so, for example, to model the fact that we have offload conditions from edge to cloud and so on, and also to have more complex problems with the multi-objective optimization problems. And these are the most recent publications that we have done with colleagues from my university and colleagues from the Catholic University of Brescia that we have done on this topic. Thank you very much.
Thank you indeed. Are there any comments?
Just a question.
Yes. Yes, please.
Just a question. When you schedule jobs for different cloud, you need to migrate them from one place to the other one. That takes some time. Do you take care about this?
No, we didn't take care of the migration problem because, as I said, we are envisioning a scenario where users have as a sort of heavy computation, so some sort of batch computation, which requires a lot of time. For example, the deadline in our case was set to 36 hours, and so we do not plan to have this situation, because it is something that users should know in advance. So it's not something that is done in real time where you can adjust and migrate tasks. Okay. So it's something that is done in advance, and users so have the idea of what resources are needed to meet to satisfy the deadline and the cost, and without having any possibility to migrate.
Thank you.
Thank you.
Thank you.
There is one parameter or one metric that, of course, would have to be included in any realistic situation is the energy costs.
Oh, yes.
Because they're very important.
Yeah, yeah.
Especially when you also consider migration, because 36 hours is fine, but it may take you, I don't know how many kilowatts or to transfer stuff. So how would you include that in this model?
The point is that for the moment we just formulate a simple problem, just to take into account the fact that we have this variability. Okay, but as I said, we are currently working on extension of this, and energy was one of the parameters that we have in mind. So we don't know exactly where exactly to put it into the model, but it's something that we need absolutely to take into account. Thank you.
Thank you. Okay, so hello everybody. So it's my pleasure to be here today. And my talk is going to be devoted to matching models. So this is based on joint works with several co-authors. Ivo Adan, Anna Buzic, Varun Gupta, Pascal Moyal, and Gideon Weiss. So what are matching models? So to start with, here is a symbolic representation of a classical queuing model. So in a classical queuing model, you have customers and servers, and both of them are quite different. So customers arrive in the system, they receive some service, and then they depart. As far as servers are concerned, it's different. They are part of the system, and they alternate between busy and idle periods. In a bipartite matching model, we have a complete symmetry between customers and servers. So in fact, it might be even more relevant to use different terminology. But okay, so we stick with customers and servers, but for instance, in the original paper introducing the models that I will mention later on, the context was that of kidney transplants. So in fact, the customers were the patients and looking and searching for a kidney, and the servers were the kidneys searching in a sense for a patient. So complete symmetry between customers and servers, and in fact, both customers and servers arrive in the system and then depart. And in fact, you will see that they arrive simultaneously and they also depart simultaneously. So here is a possible symbolic representation of a bipartite matching model. So you see that in particular you have buffers associated both with customers and with servers. So here is a more formal definition of the model. So you have customer types. C is a set of customer types, finite set. S is a set of finite server types. And you have a subset of C times S, which gives you the possible matchings between customers and servers. You see, like in the patient and kidney problem, you have some compatibility issues, which means that not all matchings are possible. Then you have arrivals. So I told you that customers and servers arrive by pairs. So you have some probability distributions on the ordered pairs of customers and servers, which tells you the arrivals. So that's mu. And you see that here we assume that the arrivals for customers are independent of the arrivals for servers. So you have a product of mu C and mu S. Mu C is the probability for the arrivals of customers, and mu S the probability for the arrivals of servers. And then you have a matching policy, because when a customer arrives in the system and there are several possible servers with which it can be matched, then you have to decide which one to get matched with. And symmetrically, when a server arrives and there are several possible customers to be matched with, then you have to define the matching policy. And here are some examples. First come, first serve, match the shortest, match the longest, some priority, random. So I'll come back to that in more details later. So time is discrete, arrivals are ID. So at each time step, you have arrival of a pair of one customer type and one server type. Servers and customer get matched instantaneously and according to the compatibility graph and according to the policy. Customers and servers that are matched leave immediately the system, and customers and servers that cannot be matched are stored in buffers. So overall, we have a discrete time Markov chain with an infinite state space describing the model. So let us look at one example with what we call the NN model. So you have 3 types of customers, 3 types of servers, and you see that, for instance, a customer of type C1 can be matched with a server of type S3 or S2, but not S1. So let us assume that for the moment we have 3 pairs that have arrived in the system, and here they are, C3 S3s and C3 S3s and C2 S3. So you see that there are no match possible. So in fact, after this arrival of these 3 pairs, we have in the system all customers and servers remain in the system. Now we have a new pair arriving, and it consists of a customer of type C3 and a server of type S1. And now there is only 1 pair that can be matched, C2 and S1, so they get matched and they leave immediately the system. Another arrival, C1, S2, now there is another possible matching. C1 can be matched, in fact, either with S3 or with S2. Now the policy has to come into account and assume, for instance, that the policy is first come, first serve. Here is a matching that will occur, and the 2 customers and server leave the system immediately. So after this, you have 3 customers remaining in the system and 3 servers. Okay, so we can describe what is a state space, and in fact there is a small mistake in the slide. The state space depends on the policy. If we have to remember the order in which the arrivals have occurred, for instance, if we use a policy which is first come, first served, then we have to remember exactly the order of the arrivals. And if we use a policy like match the shortest or match the longest, so for instance in match the longest, an arriving customer which has a choice is going to be matched with the server with the longest buffer. So in this case you don't have to remember the order of arrivals, but only the content of the number of customers and servers of each type at any given instant. So in the first case it is the first line for the buffer, for the state space of the buffer, and in the second case it is the last 2 lines. Interesting variation, so it's interesting because it's even simpler. The matching model. So in the matching model you have no pairs of arrivals, you have only one type of items, so we call them items, which arrive in the system. So and we have a graph which gives us the possible compatibilities between items. Okay? So at each time you have arrival of an item according to a low mu, and if an arriving item finds in the buffer an item with which it can be matched, then matching occurs immediately and the 2 leave the system. So once again, we have a discrete time Markov chain, and let's look at an example to be sure that we understand the model. So here is a matching graph. So we have 4 types of items, 1, 2, 3, 4. Items of type 2, 3, and 4 can be matched together, but item of type 1 can be matched only with items of type 2. And here is an example of a string of arrivals from left to right. So first you have an item of type 3, then 1, they cannot be matched together. Then a 4 arrives, it can be matched with a 3. So the 2 get matched and they leave. Then we have a 2, it can be matched with 1. The 2 get matched and they leave. And at this step, the system is empty again. And then we have new arriving items, and here is a possible description of the evolution of the buffer. Okay, so bipartite matching and matching are in fact related. So it's not, here is how it works. You start with a matching graph, and you are going to duplicate all the vertices. That is here, we have the matching graph with items 1 up to 4. You duplicate them, 1 up to 4, and 1 tilde up to 4 tilde. And you're going to put an edge between I and j tilde, if in the original graph there was an edge between I and j. Now, on the left you have the matching model. It assumes that you have arrivals. Then on the right, you assume that you will have arrivals coupled of a customer and a server of the same type. That is, a customer CI and a server SI tilde will arrive together. If you do this and if you think a little bit, you will see that what happens on the left is exactly the same as what happens on the right. But the difference is that on the right you have the customers and servers which arrive in a coupled way. Okay, so these models do not come completely out of the blue. There are some models in queuing theory which are related, which have the same flavor, but which are nevertheless different. So here are some examples mentioned here: skill-based queuing models, stochastic online bin packing models, constrained queuing networks of Tassiulas and Euphremides, input queued crossbar switches, and I'm sure there are also other ones with, again, the same flavor. Now, for the precise models I've been talking about, they were introduced in the following papers. For the bipartite matching model, it was introduced in 2009 by Caldentine, Kaplan, and Weiss, and the matching model was introduced by Pascal Moyal and myself in 2016. So, stability of the model. As I told you, we have a discrete time Markov chain. So the first question, which is natural in this context, is the model stable, or is the Markov chain ergodic? So there are some natural conditions. So they are explained here on this NN model. For instance, if you look at the first line, what you ask is that the rate of arrivals of customer of type C1 has to be strictly less than the rate of arrivals of servers of type S2 and S3, because the customer of type 1 has to be matched either with a server of type 2 or 3. Okay? If you do the same thing for all customers and servers, you have a set of conditions which are quite natural associated with the model. In fact, these natural conditions are necessary conditions for stability. That's not difficult to prove. But in some cases, these necessary conditions are also sufficient. When these conditions are both necessary and sufficient, we are going to say that the model has a maximal stability region. Okay? And it is in particular the case for the bipartite matching model with the match the longest policy. Or for the matching model, in fact, with the match the longest policy. So the proof here is not complicated. It uses a quadratic Lyapunov function. For other policies, the thing is different. So here it's slightly more difficult to prove that match the shortest, for instance, or with policy, with priority policies, it would be the same. To prove that they do not have a maximal stability region, you have to exhibit a counterexample. So that's what we did here. We proved that for the NN model with the match the shortest policy, then it does not always have, it does not have a maximal stability region. So what we did is that we proved that for some particular points for which the necessary conditions are satisfied, the model is unstable. And in fact, this is a simulation. So the triangle, the complete triangle would be the maximum stability region. And in fact, the stability region corresponds only to the yellow part. What about the most natural policy, which would be the first come, first serve? Well, in the original paper, it was conjectured that for this policy, the stability region should be maximal. It took some time to prove the result, and in fact, interestingly, the result was proved because a much stronger result, in a sense, was proved. What was shown by Adam and Weiss was that we can associate with the model some Markov chain, which is quite intricate. It's not the most natural one that you would think of given the model, but for this intricate Markov chain, it has a product form. And since it has a product form, then you know exactly what the stationary distribution looks like, and then you can deduce what are the stability conditions. The fact that this Markov chain has a product form was proved by brute force, in fact, in a sense, assuming that it has a product form and proving that the balance equations are satisfied, so that it actually works. So what we did later on with Ivo Adam and Gideon Weiss and Anna Buzic was to prove the same result in a different way with another Markov chain, which is simpler in a sense, but still not completely natural, but simpler, and proves that we have a product form with an argument which looks a little bit like Reich's argument for the simple Q. That's not brute force anymore, but it's more like a reversibility argument to prove the product form. So, next point and last point, product form and Lorenz construction. So when I prepared this talk, I assumed that when arriving at this point, I would have almost run out of time. So I decided not to give you the precise statement of what the product form looks like, because even to describe what is the correct Markov chain which has a product form would require some time. So what I will do instead is to give you some explanation of the next step. When you have a product form, it works. The next step is, do we have a Lorenz construction for the model? Or, to put it differently, can we define a first-come, first-served matching on a B-infinite string of customers and servers? So you know the idea of Lorenz construction is to define something on the B-infinite string by going backward. Okay? So if you move only forward, then it's very easy to define what is a first-come, first-served matching. But when you want to do it on a B-infinite string, then you have to start to add customers and servers in the past. And now things become a little bit more complicated because, as you see on this example, so I added in the past one customer and servers C-1, S-1, and by doing this, I change all the matchings all along the way. Okay? So even stranger things may occur. So let's look at this matching graph with 3 types of customers and 3 types of servers. On the top line, you see that we had some customers and servers arrive in a periodic way in this model, and you have complete matching, so you have 6 customers and 6 servers that have arrived in the model, and you have a complete matching among them. And then you had in the past 1 pair of customers and servers. It rearranges all the matchings, and for the first pair of customers and servers, which was previously matched, it is not matched anymore. Okay? And you see that if you do this in a completely periodic way in the past, then the first customers and servers will alternate between matched and matched, matched and matched. So you have no clear and obvious monotonicity in this model. But in fact, you have some hidden monotonicity, not that well hidden, but you have to realize this to go to the result and to go to Lorenz construction. In fact, if you, instead of looking at a precise customer and server, you look at the numbers of unmatched customers and servers, then you have some subadditivity, pathwise subadditivity holding for the number of unmatched customers and servers. This is what is formally stated in this lemma. When you use this and you put some additional well-defined stochastic assumptions on your model, then you are able to prove that there is a Lorenz construction going on, which means that you can really speak of defining this matching on a B-infinite strings of customers and servers. So since the original papers that I mentioned to you, these kind of models are kind of gaining interest in the community, so you have more and more people working on this kind of models. So this is in fact a non-exhaustive list of papers of different authors which have been looking at the model, and in fact you see that many of the tools that have been used or looked at in classical queuing theory are being reused in this context. Some control of queues, what can we do? Some fluid approximation, what can we obtain on the model by using this kind of approximation, so on and so forth. That's all for me.
Thank you. Thank you.
Yeah, I'm sorry, I think I missed something. With respect to the service rates, I saw you write service rates sub C of, etc. I would expect that the service rate is a function of both the server and the customer.
So in fact, there is no service rate because the assumption is that if you can be matched to someone, you leave immediately. Okay, so the service rate is kind of infinite, if you want.
I see. And the only requirement is matching.
Yes. You enter the system, you find a match, you leave immediately.
So what are the mu sub c's?
So mu is just the probability of arrivals. Mu of C1 is the probability that an arrival is of type C1.
So it's the arrival rate.
It's the arrival rate.
So you have a system without storage. Oh, sorry, storage.
You have storage of unmatchable
Okay, so you have a
customers
queue
and
where
servers.
all the unmatchables are all together in a big queue, right?
Yes.
Servers and etc. And as soon as they find a match, they're gone.
Yes.
Okay, thanks.
Thank you. Yes, please.
For the stability conditions, I mean, what are the assumptions, most general assumptions under which one knows the exact stability condition for these problems? Because you alluded to Lyapunov functions, but then you alluded to Lorentz. I mean, what are the cases where one knows the answer using ergodic theory? More precise formulation of the question.
So I'm afraid that my answer will not be completely satisfying. The cases where we have complete answer are the cases where we are able to actually completely compute the stationary distributions. So if we look at more general assumptions on the model, then we are not being able to prove that we have a maximum stability region. Well, the only thing we are able to do is to prove that there are some sufficient conditions for which the model is stable under any policy and under any kind of stochastic assumptions on the model. But these sufficient conditions give a very narrow stability region. So it's not very satisfactory.
Thank you. Yes, please.
In your model, you assume that when there is a match, you have to match it instantaneously and you cannot wait. I imagine that for stability, it will not change maybe much the result. But if you want to maximize some reward function, then it might be quite different.
Yes, that's certainly and absolutely true. You are not optimal by doing this because what you impose is to do the matching on the fly, and immediately. In some cases, it would be better to wait before doing the matching. That's true, but I cannot give something. I cannot give some more precise results and statements apart from the fact that you are obviously right.
The service time 0 seems a little bit unrealistic. So matching actually means there should be a service phase. How can you take that into account?
Okay, so you see, in a sense, in this model, you don't have a resource like a server that would be in use while the processing occurs. So in fact, if you think of the model, if you had some service time, it will just delay the moment when the pair of matched items will depart. But since it will not use any resources during that time, it will not really change the whole dynamic of the system.
Just a comment. Some 50 years ago, when we had the old telephone switching systems, we had the problem of what was called reachability. We had only access from an input to a number out of all servers. And there was a scheme that looked pretty similar like that, but not variable at this time, of course. There was no software. And then we looked at these things and analyzed those systems just by equations, stuff like that.
Okay, thank you. First, I have to apologize for the title because the one you have in the program is not the correct one. I'm here to talk about proactive queues, not preemptive queues. It was too late in the night when I sent my mail to the organizer. Okay, so I want to consider queues where the server can serve before the customer is arrived. Like take the example of the pizza street vendor who will just before the rush time make some pizza in advance to decrease the waiting time of the customers. So that's another example which is important is when in a workshop teams will repair subsystem of system, like they will repair engine, eventually in advance to replace the engine of a plane or of an helicopter, for example. So my objective here is to look at this type of queue, and I will start with the single server queue, and then look at the multi-server queue, and I will try to say more later. Where's the? So maybe the picture explain exactly what I mean by a proactive queue. So the upper buffer is the buffer for the customers. The process is a Poisson process. And J is just a number of customers inside the buffer. While the server is furnishing services in the small with limited capacity buffer below, and there is a maximum capacity, capital C, and I is just the number of items which are ready waiting for server. So either J is 0 or I is 0, and they may be null together, but if J is greater than 0, I is 0, okay? And reciprocally. So I will call that MM1 C Q. Okay. And I will introduce the variable k equal to C minus I plus J, such that I may consider above depth process, which is illustrated below. And you recognize the classical above depth process, and you know by heart the steady state distribution and the ergodic condition, rho. If rho is lambda over mu, rho has to be not lower than 1. Okay. So if we look at the mean number of customers, for example, the small dots mean after a few lines, and then we realize that it's rho to the power C plus 1 over 1 minus rho. That means that the expected number of customers in this proactive queue is just rho to the power C times the expected number of customers in the classical MM1. Of course, the mean response time just by little. And now if we consider the waiting time, WC, and the service time, WC, we can compute the probability to have a null waiting time, which is just 1 minus rho to the power C plus 1. And the probability to have a null service time, which is new with respect to the classical MM1, which is equal to 1 minus rho to the power C. Okay, and from these last two results, we may deduct that the probability to have a service time, a null service time, with C capacity C plus 1 is equal to have null waiting time with a capacity C. So from that we can illustrate that with the picture here where we represent, we compute the probability to have null waiting time or null service time given the value of C. Okay, this picture is just for rho equal 3/4 and mu equal 0.5. Okay. And also we can compute the expected service time, which is not 1 over mu like in the classical MM1, but here we found that the expected service time is just rho to the power C times the 1 over mu, that is the mean service time of the classical MM1. And now considering the expected waiting time, we see that it's rho to the power C times the expected waiting time in the classical MM1. And we can deduct that the expected response time given that the capacity is C plus 1 is equal to the expected waiting time given the capacity is C. So again, a new illustration for the same numerical value. And we see that it's working numerically. But if we look at the conditional waiting time, the expectation of the waiting time given that the customer will wait, then there is no progress. It's still the same as before without any proactive action. And if expected response time, given that the response time is positive, because in the proactive queue it might be 0, okay, then we see that this conditional expectation is equal to the expected response time of the classical MM1. So nothing to win on this side. Now, if we look at the cumulative distribution of the waiting time, here it's similar, a little bit similar to the classical MM1. There is a mass at t equals 0, as like in the classical MM1, except that here this mass is bigger than without capacity. And the continuous part of distribution is again an exponential one with the same rate, mu minus lambda. Okay. And if we look at the response time, then for C equals 0, there is no mass, of course. And in the classical M1, you have no null response time. And you see when you increase C, then the mass is increasing. So it intuitively makes sense, but it's interesting to know exactly what happened. So that was what I wanted to say about the single server queue. Now, if we consider the multi-server queue, here we have still Poisson process arrival with rate lambda. And here the capacity C and the service will depend on the value of the queue. Okay, so I wrote it like that. Again, we consider the variable k equals C minus I plus j. I repeat that I is just the positive value of C minus k, and j is k minus C, okay, plus. We don't have negative value, of course. Now we have to consider two cases for the birth-death process. The first one, when R is lower or equal to C plus 1, then things are simpler than the other case, just because when customers are in the queue, then the service rate is always equal to R times mu. there are customers in the queue for states starting at C+1, C+2, etc. Okay, so the service rate is constant equal to R times mu. Why? If R is greater than C+1, then when you have just a few customer waiting, look at the rate at C+1 is C+1 mu, and so on. So you have more difficulty to get the answer. But anyway, for these two types, we know the steady state probability. Okay, so the same rho is here lambda over R mu, and rho has to be lower than 1 to have a steady state solution. Now we look at the performance. The mean number of customers doesn't depend on the relation between R and C. It works the same formula for the two cases. And it's again the mean number of waiting, not customer in the queue, but the waiting customer. The expectation is rho to the power C times the expected number of customers waiting in the classical MMR queue. Of course, if we use detail, we get the expected waiting time. Now, for the nice case where R is lower than or equal to C+1, the mean number of customers is just equal to rho times to the power C times the expected number of customers in the MMR queue, the classical one. Again, by detail, we have the mean response time. Sorry, I made an error. The point is that here, it's not true that you see the expression of the expected number of customers, and it hasn't had the same presentation that before. This is not rho times C like for the mean number of waiting customer. This doesn't work anymore, okay? But anyway, we are able to compute it. And so that's the bad point, but the good point is that we are still able to express the mean number of customers in the queue as a function of the number of the expectation of the number of waiting customers for different value for C and C minus R, if C is greater or equal to R. Okay, then something which is new, it's the mean number of requests being served as a new expression here. So NS sub C is the mean, the number of customers being served, and the mean service time in that case is not 1 over mu, but another more sophisticated expression. Now, if we look at the probability that the waiting time is null, we got the expression and also the expression of the null service time, okay? And here we got a relation between the probability to have null service time and null waiting time for two different values of the capacity, of course, C and C minus R. Now, if, again, the probability, R is lower or equal to C plus 1, we are able to look at the probability distribution of the waiting time. And it's almost the same as before, that means you have a mass in 0, and the continuous time is still an exponential part with the same rate R mu minus lambda. And the same for the response time with the probability to have a null response time, which is new with respect to the classical MMR. But it's not too far from the result of the MMR. Now, if we consider the other case, R strictly greater than C plus 1, then the expressions are not so nice. you see the mean number, the expected, the mean number of customers being served, then the expression is not as nice as before, and the same for the mean number of customers. And a colleague said one time for this type of formula, I would not show them to my mother, okay? And, but given this result, if you check for C equals 0, you get again the classical result. That means that R times rho is the mean number of customers being served, and R rho plus the expected number of customers waiting is also the classical result for the MMR, the classical MMR. So we can illustrate again the relation between the response time and the waiting, the expected response time and the expected waiting time. So the 2 points which are surrounded are the case where we are obliged to use the ugly formula just before, or the nice formula, that depends how you see it. And the same for the relation with the probability to have a null service time and the probability to have a null waiting time. Okay? Always the same numerical example. Now, something interesting. It's the service time of a target customer. I call this target customer August. Okay? So given that I is greater than 0, then the service time is null, so it's just mass in 0. And now, given that I is equal to 0, then if P is the arrival position of August in the buffer, then if we are in the nice situation where R is equal or lower than C plus 1, the service time will be an Erlang of the K and rate R mu, where K is the mean of P and R. While if R is greater than C plus 1, if August is in the first position, when he arrives in the queue, he got the position 1, then the service time will be a Coxeton distribution for the R minus C, because during his service with rate which is not equal to R mu at the beginning, but C plus 1 mu, then customer may arrive and active new servers, and so active improve the service rate of August. Okay. Now, if now P is greater than 1 but lower than R minus C, then the service time follow an acyclic space-time distribution with a unique initial point. And so the distribution of the service time is given, in fact, by the transient probability of the absorbing state of this chain, okay? And here you got the red curve is the cumulative distribution of the service time of August for the previous example. Now, if P is greater than R, then I skip another case because I don't have time anyway. I was sure I would not have time. So P greater than R, there is, August has to wait before getting service. And during the time he is waiting, customer may arrive behind him and in fact improve the service rate. That means that the first arrival behind him will active new servers, okay? So that means that for the small example I used before, instead of having just one initial state for this acyclic phase-time distribution, then we have 3 initial states. So one point I will not talk about is how to compute the different probability for the 3 initial potential initial state. Okay? So, I have almost not, but okay. So just, yeah, I start late, huh? You remember, I start late. I want to say just as a conclusion that there are potential utilization in logistics, in some telecommunication protocol, in maintenance, and also that we may extend this type of model to a little bit more sophisticated with conditional arrival rate, service rate depending on I and J, and so we may have different type of function there. For example, lambda of J can be just n minus J if we have a limited population, and it will be a revisited repairman problem in this case, for example, and so on. So, and just a little remark, with this MMRQ I presented, I may study the case where we have negative customer arriving, the simplest case of the negative customer, the one who killed just the customer waiting at the end of the queue. Okay, he doesn't kill pizza. He killed the customer for the pizza. Okay, so thank you very much.
So my name is Krzysztof Gokla, and I will present some results on the performance test and evaluation of Smart City Internet of Things systems, especially in the case of representation of the linear infrastructure. So I will start with the problem formulation and the motivation for our work. Then I will describe how to represent the linear infrastructure in cities using a graph database. I will describe our contribution, which is a graph generator which allows to evaluate such systems. And I will also present how to integrate such systems based on graph databases with existing relation database systems for managing and controlling such infrastructure. And I will finish with some performance tests. So first, in current cities and in smart cities especially, we have a lot of linear infrastructure, which is basically some cables, some pipes, some construction object, something which has linear form and is located within the city. And of course we can use Internet of Things devices to monitor, to get statistics, to get some measurements about how this infrastructure works. And we can also use Internet of Things devices to control the elements of the linear infrastructure. And this work was realized as a part of a Smart City IoT project, which our institute is executing in cooperation with IoT company, which is based or coming from the smart metering market. They manufacture the smart meters and have management systems and data collection systems for metering infrastructure. But they plan to extend this into a more diverse system of network with dynamic topology for different smart city applications, coming from monitoring the infrastructure, for example, controlling the city lights and city traffic. And so a lot of companies within the city has such infrastructure, for example, district heating, water distribution network, and of course it can be represented as the graph. And very recently a lot of attention was attributed towards graph database, which allows to store and process the graph information. But as I will show later on, it is not so straightforward to use graph database for such a system. And for performance evaluation, we need some synthetic data about such infrastructure. So we can get some measurements or some big data from one or two companies which have such linear infrastructure. But if we develop a system which can be installed in hundreds of different applications, we need to do performance evaluation even for large-scale systems, or for different types of different characteristics of the topologies of the network. And for this, we need some data on which we can do the evaluation. So this was our motivation. What we have proposed is to first use the graph database, and then we have proposed how to represent such data and integrate the existing system with the graph database. So graph databases are based on graph theory. They consist of nodes, edge, and some properties attached to the nodes of the graph or to the edges of the graph. Relations are stored directly between the records. So the database already stores the information in the graph form. You don't need to create special tables to represent the connections within the graph like in traditional relational databases. And the most popular example of such database, most widely used, is Neo4j, which is a database available in open source. It is mainly used in Java language, but it can be also integrated with other languages. And there is a special language called Cypher, which is quite similar in the function to SQL or SQL, and allows to ask questions and get the data from the database. So our solution on the problem how to store the information about linear infrastructure is to use a graph database, which is most intuitive choice. But if we have such data about this linear infrastructure in the existing system, which is in most of the cases based on relational databases, we need to somehow add this graph database to the system. No one will change system managing infrastructure costs millions of euros just because we say that such new database has come. So what we can do is to integrate the graph database as an additional function added to the existing management system and use it for improvement of some operation which require getting data about the connections or getting data about the shortest path between some links in the graph, etc. So what we have developed a graph generator which can be populated from the existing relational database, and it either gets some information about the connection from existing relational database and populates it into the graph database Neo4j, or it can also generate synthetic data about the connection and about nodes to feed the data for performance evaluation. And the generator also allows us to define some synthetic structure if we don't have information about the connection in the network, which is often the case. Many of the operators of linear infrastructure have just information about the measurements as meters connected to particular location, but have no information how they are connected, at least in the database. And so for such a case, just to evaluate the system, we can generate the artificial data and generate the graph. We have proposed a presentation based on hierarchical graph with 3 layers. So because what we've observed that it's not a single graph which represents the topology of the network, it's usually a multi-graph. So it means that we have one layer of connection representing, for example, physical connection between the pipes, but then we have some additional layer of connections, for example, representing the distribution of the water or some control, which cannot be different. So to represent it easily in the graph database, we have proposed a 3-layer structure, which consists of infrastructure layer, meter layer, and device layer. But we can have a device which does some particular operation like metering and so on. The meter which is data collected about some physical objects, and infrastructure are the connections between the physical objects. And this is sample screen showing how this data are represented in the graph database. And what does the graph generator do? It's an application written in Java which creates a list of nodes with different types based on the SQL database from the current management system. It is parameterized by the configuration which defines the complexity of the generated graph, which can be changed using a configuration file. The generation for the performance evaluation proposed can have a different number of connections, different number of source and client nodes, and some hierarchy within the devices. And as I already mentioned, the application can be used twofold. First is to generate synthetic data for performance evaluation, and the second option was to populate the data from some existing system into the graph database and execute for the external clients operation requiring finding some data related to a particular part of the graph or related to finding all leaves in the tree. If we have a part of the topology which is connected to other, we can use the system to calculate aggregates. And this is another example of how the structure of the system works. And this is the representation of the graph within now from J database. And some results of the performance evaluation. So this tool can be used either for evaluation of complete system or for checking some performance of the algorithms working on graph databases. And so this is the generation time. We can see that it's much more than linear, so it's proportional to the square of the number of connections within the graph. And the generation of the graph, the fifth step before we can start asking the questions to the database, it takes quite long. Depending on the size of the node, depending on the number of the middle nodes within the network, it can take up to 1 or few hours. And it's also the complexity of the generation or importing data depends on the number of connections within the network. So for the largest case, we had 4 hours with 55,000 meter device, or 55,000 objects, and in total 86,000 devices. But it's a one-time operation. This is the operation needed to run only once during starting to work with the database. Then it's populated with the data from the relational database. And as an example, we took we integrated this with the existing system for monitoring the devices in district heating application. And then we use this for the queries to check how some operation compare, how fast the operation related to finding some data in the graph executed using graph database in our system or executed in relational database. So this is the example showing how the relational database is quick on finding the shortest path or a path between two elements in the database, and how fast does it work on the graph database. So this result shows that it's by 2 orders of magnitude faster using the graph database. So to conclude my talk, we have developed a tool for performance evaluation of linear infrastructure system and a tool for we have proposed a structure for representation of linear infrastructure in graph databases and architecture merging the graph database with relational database. The performance analysis shows that using this approach and the graph database, we can have response to some operation requiring finding shortest path or finding our leads in the tree by the 2 orders of magnitude faster than in traditional relational database, and the codes of the graph database will be done. Thank you. Thank you.